Hello. In this video, we are going to derive the sigma orbitals of boron trifluoride, BF3, using the projection operator method. We can draw the structure of boron trifluoride as follows, recalling that it is a trigonal planar molecule, which means that all four of the atoms are in the same plane, which we'll call the XY plane in this case. And each of the bond angles is exactly 120 degrees. We therefore assign it to the symmetry point group D3H. When using the projection operator method, what we do essentially in the first steps is to derive the so-called group orbitals of the external atoms. So let us represent crudely by a circle the sigma orbitals on the group atoms outside here, which are the fluorine atoms, and we'll label these as S1, S2, and S3, S standing for sigma. Later, we will determine which atomic orbitals on boron will have the proper symmetry to interact with the linear combinations that are found by symmetry on the external fluorine atoms. Next, we make a small table which has the same structure as the character table for the point group D3H. We have the point group listed in the upper left-hand corner, and each of the columns represents one of the symmetry classes in the point group. And we see that in D3H there are 6 different classes. We also see that, for example, in this particular class here, we have 2 C3 operations. So the new number that is in blue tells us how many operations are in the class. Also, we see for C'2 that there are 3 operations in the class. For 2 of the columns, we see that there is no number at all. By implication, when there is no number, we assume the number 1, just as we commonly do in algebra. For reasons which will be clear in a minute, I will actually write in a number 1 for each of these columns so that what we do later on is more clear. Next, we want to generate a reducible representation. So the symbol that we use for a representation is a capital gamma, the letter G in Greek, and we can make a subscript with sigma to show that this is a representation regarding the sigma orbitals of boron trifluoride. Then the character that we put in each class in the table is precisely the number of these s orbitals, the S1, S2, or S3, that do not change under the symmetry operation. So for example, the first symmetry operation is E, the identity. So in the identity, nothing moves. So we have 1, 2, 3 orbitals that don't move. So our character is going to be a 3. For the C3 operation, the C3 axis comes perpendicular to the plane of the whiteboard. So that would take orbital S1 to S2. S2 would go to S3, and S3 would go to S1. Since each of the orbitals has moved, none of them stay still, so our character is going to be a 0. Now for the C'2 axis, that is essentially along this stick. So along this particular axis, S1 turns into S1, S3 turns into S2, S2 turns into S3. And the same situation will occur for the other 2 of the C2 prime symmetry operations. So if we go along this particular axis, S3 stays put, but S2 and S1 would move. So in any of the three cases, we see that exactly one of the orbitals will stay put, the other two will move, so our character is a 1, because one orbital does not move. Our next symmetry operation is sigma h. This is a horizontal mirror. So our high order rotation axis for D3H in this particular case is coming perpendicular out of the whiteboard. So perpendicular to that, normal to that, is the plane of the whiteboard. So our mirror here is the plane of the whiteboard. So that reflects S1 into S1, S2 into S2, and S3 into S3. So since they all stay where they were, our character here is going to be a 3. Our next to last symmetry operation is S3. This is an improper rotation of a third of a circle. So S3 consists of a C3 operation moving S1 to S2, followed by reflection in the plane of the whiteboard. So S3 would take S1 to, this S3 here, would take orbital S1 to S2, would take S2 to S3, and take S3 to S1. So all three of those orbitals would move, which means none of them stays put, so our character is going to be a 0. And last but not least of our symmetry operations is a sigma v. We have a vertical mirror. So the vertical mirror in this case is a plane that is perpendicular to the whiteboard. So the first of these would go along the x-axis as we've shown here. So that would reflect S1 into S1 because it's along the symmetry axis. But it would reflect S2 to S3 and S3 to S1. So this would be our second sigma v, and this would be our third sigma v. So we see in each case, we would have exactly one of the orbitals would stay where it was because it's along the symmetry axis, and the other two would move. So our character in this case would be a 1. And we see in green, we have determined the characters of the reducible representation for the sigma bonding in boron trifluoride. In the next step, we want to reduce the reducible representation into a linear combination of the irreducible representations in the point group D3H. At this point, you want to make sure that you have by your side to consult either a printout or an online version of the character table for the point group D3H, since for the sake of clarity and to save time, we're not going to write that character table out on the board at any one time here. So, but we're going to use that information. So, to figure out how many of each of the irreducible representations that we have, we apply the great orthogonality theorem. So, we have to go one by one through each of the irreducible representations. And in D3H, there are 6 such representations. And we have this particular formula that we use. And to make the formula clearer, I've color-coded each of the terms to make it clearer where each term is coming from. So the first term is we have this 1 over 12. And the reason why we do this, this is the number, 12 is the number of symmetry operations in the group, which we call the order of the group. So no matter what problem we're working with when we're doing this reduction of a reducible representation, we always have this factor in front, 1 over the order of the group. So that's where the 12 comes from. 1 plus 2 plus 3 plus 1 plus 2 plus 3 is 12. That's the number of symmetry operations in D3H. So then we have a series of terms. So the first factor is always going to be the character of the reducible representation. So that is the 3, and that's in green. The second factor in the term is the number of symmetry operations in the class. And we see that for E, the number of operations in the class is 1. And you see now why I actually wrote the 1 in there explicitly so we could see where this number was coming from. And the third factor we don't see here, we're going to write in red, comes from the character in the character table. So if we look under E for A1 prime, which is the first irreducible representation that is listed in the table, we see that the character is a 1. So our first term is 3 times 1 times 1, and we see by the color where each of those terms has come from. Now, when we get to the second class, we see a way that we can save ourselves some work. Because the second term should be taking the character from the character table 0 times 2 times the character in the irreducible representation from the character table, which is a 1. So you'd have 0 times 2 times 1. But we can use the fact that multiplying anything by 0 equals 0. So we can save ourselves some labor. Anytime we have a 0 in the reducible representation, we can simply omit this entire term, or we can write it out, but we're going to get 0 for it anyway. So now the next non-zero term in our reducible representation is under the 3C2 prime. So our character from the reducible representation is a 1 in green. The number of operations in the class is 3, so we write that in blue. And the character from the character table for A1 prime is a 1. And again, what you'll learn by practice is that the first irreducible representation in any group is always going to have all 1s as characters. We call it the totally symmetric representation. So you don't necessarily even have to look at the details of the first irreducible representation to know that all the characters have to be 1. So now the next non-zero character is for the sigma h, the horizontal mirror. So the character is a 3. The number of operations in the class is 1, so we write that as in blue. And the character in the character table is a 1. And our last non-zero term is going to be for the sigma v's. So we have the character is a 1. The number of operations in the class is 3. And the character from the character table is a 1. So now we multiply all these terms out. We get 3 times 1 times 1 is 3. Got 3, 3, 3, 3. So 3 plus 3 plus 3 plus 3 is 12. 1 divided by 12 gives us that we have 1 A1 prime in the reducible representation. It is important to double check your answer. If you ever get a number that is negative or a number that is a fraction, you have made a mistake. The only possible correct answers we can get for the number of irreducible representations in a reducible representation is either 0 or a positive integer. So we see in this case that we have determined that we have 1 A1 prime in our reducible representation. And now we have to continue with the 5 remaining irreducible representations to see how many of each are in our reducible representation. Essentially, we're determining that our reducible representation is a linear combination of irreducible representations, and we're trying to figure out how to write it as that linear combination. So now we continue the procedure for the irreducible representation A2 prime. So as we did before, the first factor is going to be the character from the reducible representation. That's our 3. The second factor is the number of symmetry operations in the class, which is 1. And our third number, which we're going to write in red, is the character from the character table, D3H. And that will be different depending upon which irreducible representation we have. So the character here is again going to be a 1. Now for the second term, which is coming from the C2 prime, the character from the reducible representation is our green 1. The number of operations in the class is 3 times 3. And now the character from the character table for the irreducible representation is a -1. Then we have 3, which is from the character there. The number of operations in the class is 1. And then the character from the character table is a +1. And our final term, we have the 1 from the reducible representation. the number of operations in the class is 3, and the character from the character table for this particular class is going to be a -1. When we simplify this expression, we see that the number of A2 primes that is stored in the reducible representation is actually equal to 0. And now I can show another labor-saving device, or if not a labor-saving device necessarily, and also a good way to double-check your work. When you're reducing the reducible representation, and you have this series of factors and terms, in every term, the first 2 factors will always be exactly the same because they come from the reducible representation and the number of symmetry operations in the class, which doesn't change. The only number that will change in each of the lines here, say going from A1 prime to A2 prime, is the third number. So the number that we've shown in red, because that comes from the character table for the irreducible representation, and these will be different, or can be different, going from line. So we see that the first red is a positive 1, but now we see that the second red number is either a 1 or a -1, and that's because we have different irreducible representations. So to save time in the description of the following irreducible representations, I'm just going to write down the first 2 terms identically for each of the irreducible representations, because we see now where those come from. And the only number that will change will be the red number, because that will be specific to the specific irreducible representation. Our third irreducible representation is E, which is a doubly degenerate representation. So now we're going to put in the characters from the character table, and the character for the E operation as a character of 2, and you'll see that that's not a surprise because whenever we have a E doubly degenerate representation, the character will be a 2 rather than a 1 or a -1. Character here is going to be a 0. The character here is a 2, and the character for the sigma v is going to be a 0. So now if we simplify this expression, we see that there is exactly one E, should be E prime here, sorry, E prime, irreducible representation in the reducible representation for the sigma bonds. Now for the irreducible representation A1 double prime, the characters we need here are going to be a 1, a -1, and a -1. So that gives us that there are 0 A1 double primes in our reducible representation. Now for A2 double prime, the relevant characters are going to be a 1, a -1, a -1, and a 1. And when we simplify that out, we see that there are 0 A2 double primes in our reducible representation. Again, we get the red characters from the appropriate characters in the character table for D3H, looking in the row A2 double prime, which is our irreducible representation that we're looking for. Last but not least, we have the irreducible representation E double prime, and the relevant characters are going to be a 2, a 0, a -2, and a 0, which gives us that there are no E2 double primes in our reducible representation. So after all this, what have we figured out? Well, we've determined that we can reduce the gamma sigma, our reducible representation. We can write it as a linear combination of A1 prime plus E prime. So that's our achievement so far, is to reduce our reducible representation for the sigma bonding into a linear combination of irreducible representations. In the next step, we're going to show how to use this information to determine what the sigma orbitals actually look like for boron trifluoride. This is now the step where we actually begin to use the projection operators. And we have to write a table, but notice that this table is slightly different than our previous table. In our previous table, we had one column for each class in the point group. This table, we have one column for each symmetry operation. So each operation gets its own column. So instead of having 6 columns, we now have 12 columns. And what we're going to do in this particular step is to take one of the representative sigma orbitals, which we'll call S1. Doesn't matter which one we do, but it's convenient to use the S1. And we want to see how this orbital is transformed by each of the symmetry operations of the group, which sounds far more complicated than what we're actually really going to do. So, if we take the identity on S1, it turns S1 into S1, because that's what the identity does. So we just put down S1 in the column E. So now we have C3. Well, the C3 operation is a rotation by 120 degrees. So that takes S1 into S2. Now notice we have two different C3s. They were in the same class in the point group, but there are two different C3 operations. One is going C3 counterclockwise. One is going clockwise. Or we can think of it as C3 followed by C3, so we have C3 squared. So that takes S1 to S2 and then to S3. So for C3 squared, the effect is S3. Now for C2 prime, that is along this kind of an axis. So that flips S1, since it's along the axis, to S1. If we look along this C2 prime axis, rotates S1 goes to S2. And then if we go along this particular axis, it takes S1 to S3. Similarly, if we have sigma h, that's a mirror in the plane of the board, again takes S1 into S1 because it's along the mirror plane. S3 is a C3 followed by reflection, so that takes S1 to S2. S3 squared kind of works the same way as C3 squared did, that we do an S3 and then another S3, so that takes S1 to S3. Apologize for using S3 to mean two different things there. But the S3 operation takes the S1 orbital to the S3 orbital. Then we have sigma v's. Sigma v is a plane going perpendicular to the plane of the board, but through the boron-fluorine axes, so that the first sigma v takes S1 into S1 because it's along the mirror plane. If we have this sigma v, it reflects S1 to S2. And then last but not least, if we look along this sigma v, it reflects S1 to S3. So what we have seen is, for any one particular orbital, how it transforms under the different symmetry operations of the class. And so long as each of these three orbitals ends up in the table, that tells us we could have used S1, S2, or S3 as our representative example. Another way of saying the same thing is S1, S2, and S3 are symmetry equivalent. So long as that happens, our results here are perfectly good. So now, in the next line of our table, we're going to write down the relevant characters from the character table for D3H for the irreducible representation A1 prime. The reason why we did that is we found that when we reduced the reducible representation, we found that it had one A1 prime and one E prime. So first we're going to do the A1 prime, and we write down the characters from the character table, which are all, very conveniently, equals to 1. And what we do now is we're going to multiply the factor in the second row times the term in the first row. So this may look trivial, but this is what happens when we have the totally symmetric representation A1 prime. So 1 times S1 is just S1. We have S2, S3. As you can imagine, it's obvious multiplying by 1, but let's write these down just to show where we get these terms from. Well, the subtle point here is after we've multiplied the first row by the second row, we are taking the linear combination. So we're adding together all these terms. And what we get is, we see that we have 4 S1s plus 4 S2s plus 4 S3s. And this is equivalent to having a wave function, and if you have a wave function solution to the Schrodinger equation, then any factor of that is also a solution. So effectively we can divide through by 4, and this gives us the orbital S1 plus S2 plus S3 without normalization. If you know how to normalize it, then you could apply a normalization constant in front. Not going to make a difference as far as to our visualization of what the orbital looks like. The important thing here is that how we interpret this particular orbital is that we are looking at the magnitudes of the coefficients. They're all 1, so they all have exactly the same magnitude. And they're also all positive. So that tells us that they all have the same phase. So we will draw these in a second, what they look like, but for the time being, we interpret this as all 3 of the s orbitals having exactly the same phase in this A1 prime sigma orbital. Now we do the same thing for the E prime irreducible representation. We copy down the characters from the irreducible representation. Now we have to be very careful because we have to make sure that we put the right character in the right column. For example, we know that if we look in the character table, 2C3 will each have a character of -1. So all the symmetry operations in the same class will have the same character. So since C3 and C3 squared are in the same column in the irreducible representation, the character table, they will have the same irreducible character -1. Also, make sure that we put down 0 for all 3 of the C2 primes. So just be careful of that you put the correct character in the right column of this particular table, because this table is laid out slightly differently than the table that you will see in your reference book. Again, we do the same thing that we did for A1 prime. We're going to multiply the factor in the second row times the term in the first row. So what does that give us? Well, we get 2S1 here. We get minus S2 minus S3. Anything multiplied by 0 is 0, so that's not a problem. Then we have plus 2S1 minus 2S, sorry, minus 1, minus S2 minus S3. So what does this give us? If we add these together, we get 4S1 minus 2S2 minus 2S3. And again, we use the principle that a solution to the Schrodinger equation, if we divide through by a non-zero constant, will also give us a solution to the Schrodinger equation. So this gives us, in reduced form, we have 2S1 minus S2 minus S3. So a way to interpret what this orbital looks like is the S1 orbital has twice the magnitude of the coefficient, so it's going to be twice as big. The S1 orbital has a positive phase, and then the S2 and S3 orbitals have the opposite phase, so they'll be negative phase. So we'll draw what that looks like in detail in a second, but just kind of how we interpret the coefficients by their magnitude tells us the relative size of the orbitals, how they contribute to the molecular orbital, and then the sign tells us the relative phases. But there's actually a more difficult problem here in that E prime is a doubly degenerate representation, which means it tells us about 2 molecular orbitals, and so far we've derived 1 molecular orbital. So now we'll show how we can determine what the other molecular orbital looks like in the E prime pair, and then the last step is we'll actually draw out what the molecular orbitals look like based upon our algebraic expressions. Now, the reason why we have a degenerate representation in the first place in the point group D3H is that we have a high order rotation axis. We have a C rotation that has a value of 3 or greater. So whenever we have a C3, C4, C5, C6, we are going to have degeneracy as a result. So since degeneracy led us to the situation of having two orbitals, but only one algebraic expression, we're going to use the degeneracy, the C3, what caused degeneracy in the first place, to help find the other member of this pair. So there's a two-step process. In the first step, we apply the C3 operation to each of these terms. So we know that if we just take S1 and we do a C3 operation, it turns S1 into S2. So if we do a C3 on 2S1, it turns it into 2S2. So we make sure that we think of the symmetry operation as a linear operator, and we can pull the coefficient out in front. So if I do a C3 on 2S1, it turns into 2S2. So let's write that down in the second line. What happens if I have S2? Well, C3 will turn S2 into S3, so it must turn minus S2 into minus S3. So we're going to use the fact that the C3 operator is a linear operator. And then last but not least, if I do a C3 on S3, it turns it into S1. So if I do the C3 operation on minus S3, it turns into minus S1. Now, what we might think is this second line we've written down here is the other orbital. But effectively, all we've done is rename the orbitals that we have. So what turns out is, while we had to do that step initially, we subtract this expression from the first expression, and that will actually give us the other member of the E prime pair. So again, being careful to handle the negative signs carefully, we get minus a minus, so this gives us 3s1, and then minus 3s2, and then 0. And again, we're going to use the fact that we can divide through by a constant and not change the orbital. It'll still be a solution to the Schrodinger equation. So this gives us s1 minus s2. So the other member of the E prime irreducible representation, in addition to 2s1 minus s2 minus s3, is s1 minus s2. So now we've found all three of the sigma orbitals for boron trifluoride. So we're going to show first what those look like in a more physical way, and then determine which atomic orbitals on boron have the proper symmetry to interact with those molecular orbital combinations. First, we're going to do A1 prime, and we saw that the algebraic expression was S1 plus S2 plus S3. So that tells us that the contribution of each of the s orbitals is exactly the same. So imagine I actually had good artistic ability, and I was drawing each of these circles to be exactly the same size. And we're drawing them to all have the same phase, so either have them as open circles to be white, or we'd have them filled in to be the other phase. But since S1 plus S2 plus S3, they're all positive, we're all going to show them as having exactly the same phase. So which atomic orbital on boron has the right symmetry to interact with these three sigma orbitals on fluorine? Well, the only combination that works is if we have a 2s orbital on boron. So we notice that in this direction, the orbital on boron has exactly the same phase as fluorine, so that's a bonding interaction. In this direction, it's a bonding interaction. And in this direction, it's a bonding interaction. So in every possible direction, this is an all-bonding sigma orbital. And that gives us the A1 prime molecular orbital for boron trifluoride. So now we have the doubly degenerate E prime combination, and we saw for the first algebraic expression we had 2s1 minus s2 minus s3. So the first thing I'm trying to draw here is that this particular orbital is twice as big as either of these two. So hopefully I've gotten that part. And then we notice that since this is plus 2s and these are minus, these have to have the opposite phase. So I'm going to color them in, which kind of obliterates the fluorine, but by reference we remember that's where fluorine was. So we see the difference in phase here between the positive coefficient and the negative coefficient. That comes about because of the phase difference in the orbitals. So what would the atomic orbital on boron be that has the right symmetry to interact with this linear combination of atomic orbitals? Well, it's a little tricky to draw here, but we need a p orbital that goes in the x direction, and it has to have a positive phase towards this fluorine atom, and then a negative phase in this direction. It has to have opposite phases because that's what a p orbital does. It has the two different lobes have different parity. There we go. So now we notice that for this side, they have the same phase, so that's a bonding interaction. In this direction, they have the same phase, both negative, so that's a bonding interaction. And then the molecular orbital goes from having negative phase to positive phase. And we know that orbitals are continuous functions. To be a solution of the Schrödinger equation, it has to be doubly differentiable. So it absolutely has to be continuous. So that means there must be some point where it goes from negative phase to positive phase. It must go through zero. So I've kind of just drawn there a sketch in purple there where the node is. So while as the A1 prime had no nodes, it never passed through zero. When we have at least the first of the E prime molecular orbitals, we have a node going this way. So this will be along the y-axis, the way we've drawn it so far. So now we have one more sigma orbital combination, and this was the S1 minus S2. So let's see what that looks like. So we have S1 and S2. They have the same size because the coefficients are both 1, but since it's S1 minus S2, we have to have this particular orbital have negative phase. So, which atomic orbital on boron has the right symmetry to interact with each of these two? The only one that does is, since we have px here, we've already used the 2s orbital, we imagine that we're going to need to use the px, py. So, py orbital. So, it has a lobe here that is negative phase to interact there. It has a positive phase to interact here. Also has to have, I'll just draw it in blue this time. Since we're going from negative phase to positive phase, it must pass through zero at some point because it's continuous. So we see here that even though these two molecular orbitals are degenerate, they have exactly the same energy. It is not immediately obvious when you look at them that this particular molecular orbital has exactly the same energy as this one does. Whenever you have a doubly or triply degenerate orbital set, they have to have exactly the same number of nodes. So since this orbital has one node, this one absolutely has to have one node. If you ever derive it in such a way that there is a different number of nodes, you have certainly made a mistake. So, we notice that on boron, we've used the 2s atomic orbital, we've used the 2px and the 2py, and we might imagine what happened to the 2pz orbital. Well, if we assume that there is only sigma bonding in boron trifluoride, then there is no combination that will interact with pz, and pz, we would imagine, will stick perpendicular to the board. Well, we recall that boron trifluoride is a catalyst for the Friedel-Crafts reaction. It's electron deficient. It's a very strong Lewis acid, and its Lewis acidity derives from the fact that it has this empty pz orbital, which is available to accept a lone pair. So as long as we imagine this is the structure, and we imagine that there is no pi bonding involved in boron trifluoride, then we simply account for the pz orbital as a atomic orbital that remains on boron and does not interact with fluorine at all. It just remains as an empty atomic orbital and is not part of any of the molecular orbital combinations. I thank you very much for your attention. Be sure to like or subscribe. Have a good one. As always, I thank you very much for your attention. Have a good one.